select is, forgive me if I didn't do this the other day, is problem number 25. It goes like this. A 50-kilogram satellite circles the Earth in an orbit with a period of 120 minutes. What minimum energy is required to change the orbit to another circular orbit with a period of 180 minutes? Alright, so you're a 50-kilogram satellite, you go around the Earth in 2 hours. What energy do you need to add to that satellite in order to make your orbit 3 hours? To solve this, we're going to need a couple important equations from the other day. One is Kepler's third law. The third law looks like this. Time period for the satellite to go around a central body, that time period squared is equal to 4 pi squared over gravitational constant, mass of the central body, Kepler's constant, times the average radius of that orbit, Q. So Kepler's third law helps relate the time of the orbit to the radius of the orbit. And in this case, we're going to need that because we're given the time of the orbit. Other developments from last time was that for a moving satellite, that we're bound with a certain energy, and for a moving satellite, that binding energy is equal to negative g times mass of the central body, mass of the satellite, over 2 times r. Well, r is the radius of the orbit. And if you're stationary, then your binding energy is just equal to your potential energy, Gmm over r. Not too many satellites are really stationary, so in this case, we're going to use this. And the reason why this binding energy is less in magnitude than this is because this moving satellite has kinetic energy. And that is reducing the amount that is being bound to the central object. So I think those are our essential equations. And for this problem, we're going to use these two. So we have a 50-kilogram satellite circling the Earth. Mass of the satellite is 50 kilograms. And the period of time in this orbit, let's call this radius r, is 120 minutes. 60 seconds per minute. What is that, 7,200 seconds? Not sure if I'm thinking right. 7,200 seconds. So, for that time, and this situation, and we're Earth, and Earth, the mass of Earth is 6.0 times 10 to the 24 kilograms. So let's use Kepler's third law to find the radius So when I reverse engineer this, I would have that R cubed equals G mass of Earth, period of time squared, over 4 pi squared. Or R is equal to G mass of Earth, period squared, over 4 pi squared, cube root. 6.67 times 10 to the minus 11 times 6 times 10 to the 24 times 7,200 squared over 4 pi squared cube root. I got 8.07 times 10 to the 7 meters. So we could probably say that the energy of that orbit, let's call it energy 1, would be equal to negative G M M over 2R. That would be a negative 6.67 times 10 minus 11 times the mass of Earth, 6 times 10, 24 kilograms, times the mass of the satellite, which is 50 grams, over 2 times that radius. 8.07 times 10 to the 7 meters. Now be the binding energy of this orbit. One of the biggest challenges is just to make sure that you punch everything correctly into your calculator. I got 1.24 times 10 to the 9. Might need a few more digits, so I need to keep 1.2398 times 10 to the 9 joules, negative. Let's try the same thing for the other orbit. The other orbit, the only thing that's changed is that we're taking 3 hours to go around. So we're at some second radius, R2, and at that radius, it's taking 3 hours to go around the Earth. So orbit 2, T2 is equal to 180 minutes, 50 seconds per minute. The 1,800 seconds. This formula should apply. So radius 2 is equal to G mass of Earth, time period squared, over 4 pi squared, cube root. That's going to be 6.67 times 10 minus 11. 6 times 10 to the 24 over 10,800 squared over 4 pi squared. All this cube root. I got 1.057 times 10 to the that doesn't look right. Try that again. Seven. Well, that means that this is probably wrong. All right, we went back. This should have been to the 6. That's going to change this. Well, it doesn't change it too bad. This is to 10. Good, that wasn't too painful. All right. So we got this. Let's figure out the energy for the second orbit. Negative G M M over 2R for the second orbit. Negative 6.67 times 10 minus 11. 6 times 10 is 24 kilograms for the Earth. 50 kilograms for the satellite. Over 2 times this radius of orbit. 1.0574 times 10 to the 7. All that negative. We got negative 9.46 10 to the 8 joule. All right, 9.46 times 10 to the 8. Does that look right? So, here's our original energy. We're bound to the Earth by this much energy. This is how much energy it would take to escape Earth from that orbit. Then we add some energy, and we actually have, we're bound less to the Earth. So this is actually a more energetic orbit because we only need this much energy now in order to escape Earth. So in terms of the amount of energy that we had to add to go from one orbit to the next, that'd be the difference between these two. In other words, our change in energy is energy 2 minus energy 1. And so that'll be negative 9.46 times 10 to the 8 minus negative 1.234 times 10 to the 10. I got 1.14 times 10 to the 10. I hope that's correct. No. Let me check this number here. 6.67, 10 minus 11, times 6 is 24, times 50. .94 times 10 to the 8 joules. More like it. See? Simple. Get a calculator that uses scientific notation. Mine just puts a bunch of numbers there, and I have to count how many places it is. Probably can figure out, put it in the scientific notation. That would help. Planet Rotan has a mass of 4 times 10 to the 23 kilograms and a radius of 2 times 10 to the 6 meters. At what speed should a space probe be launched from the surface of Rotan so as to achieve a maximum distance of 3 times 10 to the 6 meters from the center of Rotan?
Do you have enough room there?
No, don't have enough room. Here's planet Rotan. Just happens to be cube shaped. And we wish to take off from the planet well, not a good idea to make a cube shape. Because it has a radius. The mass of Rotan is 4 times 10 to the 23 kilograms. And has a radius of 2 times 10 to the 6 meters. So it's about 1/3 as, at least in radius size, the size of Earth. And we want to start from the surface of Rotan, and we want to end up at some distance called R2 that's equal to 3 times 10 to the 6 meters. So this is not drawn the scale because I guess 3 times 10 to the 6 would only be 50% more Rotan's radius away from the planet. Let's treat it like this. Here's point A, and here's point B. And whatever energy we start off at point A, we're going to have at point B because there's not going to be any dissipative effects along the way. So we'll treat it like that. Energy at A should equal to energy at B. The kinetic energy at A plus potential energy at A should equal to kinetic energy at B plus potential energy at B. The kinetic energy at A, we're just taking off. So we've got our initial velocity. We're leaving the launching pad. Well, we've got initial velocity, so we have kinetic energy, and we'll say it's 1/2 the mass of our spaceship times our initial velocity squared. Our potential energy at A is due to our gravitational binding to Rotan, and so that's going to be a negative G mass of Rotan, mass of the spacecraft, over our distance from the center of mass of Rotan, which at this moment happens to be the radius of Rotan. We're on the surface of Rotan. So that's potential energy of binding at that point. That should equal our kinetic energy at B, 1/2 mass times velocity at B squared, plus our binding energy at B, which will be a negative G mass of Rotan, mass of the spacecraft, over our radius at that point. We just call it R at B. Right. So it's kinetic energy plus potential energy, kinetic energy plus potential energy. But in this problem, we're taking off from Rotan. We're just barely making it to this point B. We just barely made it out there. So, what can I say? Velocity of B is 0. Correct. And, the mass of this satellite wasn't given, the space probe, but we don't need it here because actually in all 3 terms that remain, we've got that mass. So let's divide through by the mass of the space probe and get rid of it. All right, so now this equation looks like this. 1/2 our initial velocity squared is equal to negative G mass of Rotan over radius of B plus G mass of Rotan over radius of Rotan. Or initial velocity squared is going to equal 2 times G times the mass of Rotan times 1 over the radius of Rotan minus 1 over radius of B. Take the square root. So our initial velocity will be the square root of all this. 2G mass of Rotan, 1 over the radius of Rotan minus 1 over the radius of point B. That's 2 times 6.67 times 10 minus 11. Mass of Rotan, 4 times 10 to the 23. More room this way. 1 over the radius of Rotan, which is 2 times 10 to the 6, over a radius of b, which is 3 times 10 to the 6. All that square root. Meters per second. Or 3 kilometers per second.
And if it wanted to escape that, it would need to be square root of 2 faster.
Well, good question. We, at the end of this takeoff, we're not in a stable orbit. Because we just barely made it out there, and we're not actually moving. So we're not in a stable orbit, so that square root of 2 thing doesn't apply yet. All right? You have to be in a stable orbit to begin with. What do you think about these problems? Rocket science. A few of these problems you can say you've done rocket science. I'm a rocket scientist. Pretty impressive. Ready for something a little bit new, different? Solve problems involving Archimedes' principle of buoyant force. Identify the equation of continuity and use it to solve problems. And identify Bernoulli's equation and use it to solve problems. So we're basically going to study pressure. What's that? Oh, really? Have you done Bernoulli's equation and differential equations recently?
Well, no, we did, yes.
Oh, at the beginning of the semester. Neat. Well, then, now I'd be interested in how it's different in the two approaches. So, we're going to solve problems involving depth, Archimedes' principle, continuity equation, Bernoulli's equation. Before we get there, we need to set up a few guidelines for how we're going to approach fluids. And start by classifying matter. We normally classify matter in 3 states. We have a solid. If you have a solid piece of something, it has a definite volume and shape. So it's pretty obvious when you have an object that is solid, that it has formed its own shape and takes up its own volume. A liquid has a definite volume as well, but no particular shape to the liquid. The liquid will assume the shape of its container. So it'll be moving around and depends on what the container looks like. A gas has no definite volume and no definite shape because the pressure of the gas could change. So it will also assume the shape of its container for whatever extent that is. There's actually a 4th state of matter, which you probably haven't heard too much about. But there is a 4th state of matter, and it's called plasma. Now, plasma is a gas, but the gas of charged particles. So the particles within the gas are interacting with each other because of their electromagnetic charge. And you think, well, you know, why am I even mentioning this? Because, I mean, most of the time we just have those three states of matter, and you don't deal with plasmas on a daily basis. Plasma might look something like this. The reason I mention it is because 99% of the universe is plasma. The three states that we're most familiar with is only a small fraction of the matter in the universe. Most of the matter in the universe is in stars. Right? Various stars of various forms, and that's in the form of plasma. Gases of charged particles moving around. So 99% of the universe actually is in the fourth state of matter that we almost never talk about. And we're not going to talk about it after this. Liquids and gases themselves are called fluids. And a fluid is a collection of molecules that are randomly arranged and held together by weak cohesive forces and forces exerted by the walls of a container. In plain English, a fluid will take on the shape of this container. A liquid definitely does that, and so does a gas. So they're both fluids, and that's what we're going to focus on in this chapter. To deal with fluids in a manner that we're accustomed, we need to reaffirm some definitions. And one is density. We define density as the mass per volume of something. And it would look like this. If we use the Greek letter rho, use that for our density. And we'll say that density is equal to mass per volume. Makes sense. That would apply to solids, liquids, and gases. That would be your density. What is nice here is that we actually want to deal with fluids in terms of masses, because that's what we're accustomed to. We've been dealing with mechanics, and we want to apply our knowledge of mechanics to a fluid. So, with this definition of density, we're going to rearrange it and write it like this. We'll say that the mass of something is equal to its density, which is a constant, you know, if it's not under changing environmental conditions, times its volume. So mass equals density times volume, and we're going to use this to help us describe fluids, so that we can just think of fluids in terms of pieces of different mass. Pressure is also a concept that we wish to apply for fluids. Pressure is a compression-like stress applied to a fluid, and its definition looks like this. We define pressure as the force applied over a certain cross-section or a certain surface area. Force applied over a surface area. So if I were to submerge this object within this fluid, there would be a certain amount of force applied by the fluid on the surface area of that object, and I would define that as being pressure, force over the area of that object. Unit of pressure is the Pascal, and that would be a Newton per meter square. But again, I want to put things in terms of what I'm familiar with, and up to this point in mechanics, I'm familiar with forces. So I'm going to rearrange this pressure definition and say that my force is equal to pressure times area. So if I have a pressure somewhere and it's being exerted over a certain area, I can define a force as the pressure times the area. Here's a conceptual example of pressure. person laying on a bed of nails. If you had a bed of nails, you could create that bed of nails. Maybe if you just put one nail into your bed of nails, that might not be a good idea, because if you were to lay down on that, you would have most of your weight being exerted over the surface area of the tip of that nail. Hence, you'd have a very small area with very large force, and your pressure would be pretty high, and it might puncture through. As opposed to creating a bed of nails that had a bunch of nails going up, in which case you would have a lot of surface area on each tip of nail added together, and with every nail that you add, you would reduce, you would increase the area, and hence reduce the pressure at any particular point. Hence, you could actually lay down on that bed of nails, and what's that? Let a car drive over you. Let somebody take a sledgehammer, hit it on your stomach or something. In any case, you get the main effect of the acupuncture, and you realign your chi. Feel better. I used to have a bed of nails. A student made one for me, and somehow it didn't survive the. When we were in the old building a year ago, it didn't survive the trip from the old building here, and I feel bad about that now. I wish I would have salvaged it, but that bed of nails had really sharp nails. So, and I never had a chance to go in there just to kind of dull the tips a little bit. So every time I demonstrated that, you could do it, but I'd end up, ruining my shirt because there'd be all these puncture marks in my shirt. Snowshoes. Where I originally come from, in Minnesota, where it snows a lot during the winter, a lot of times you get these drifts, and they might be 6 or 7 feet deep. And if you want to get from point A to point B, then you could try to trudge through those drifts and sink down maybe 3 feet into the snow or more. Or you could put on snowshoes, and that would distribute your weight over more area, hence reduce the pressure, and you might just sink maybe 3 inches into the snow, and you can walk on top of the snow drifts. Not everybody in Minnesota has snowshoes. That's kind of a neat thing to do after a big snowstorm, is to kind of walk around on top of the snow. Let's try this problem. It's actually a problem from your book. What is the total mass of the Earth's atmosphere? The total mass of the Earth's atmosphere. We can actually figure that out based on pressure. The radius of the Earth is 6.37 times 10 to the 6 meters, and the atmospheric pressure at the surface of the Earth is 1.01 times 10 to the 5 pascals. That's probably a good number to remember. The atmospheric pressure, normal atmospheric pressure is actually 1.013 times 10 to the 5 newtons per meter squared, or Pascal. If we treat that at the Earth, at the surface of the Earth, what you feel in normal atmospheric pressure is the weight of the atmosphere above you, and it's bearing down on the surface area of the Earth. So we can think of the weight of the atmosphere on the surface of a sphere of the Earth, and then use that to calculate what that weight is. In other words, we know the pressure, which is force per area, or weight per area. We can calculate the weight of the atmosphere. So the force of the atmosphere is the weight of the atmosphere, and that should equal the pressure of the atmosphere times the surface area of the Earth. So the mass of the atmosphere is equal to the pressure times surface area over G. Pressure is 1.01 times 10 to the 5 newtons per meter squared. The surface area of a sphere is 4 pi r squared. So put in 4 pi radius of the Earth squared over 9.8. And we get that the mass of the Earth's atmosphere is 5.27 times 10 to the 18 kilograms. And the mass of the Earth is about 6 times 10 to the 24 kilograms. That means that the mass of the atmosphere is about 1 millionth the mass of the Earth itself. In terms of pressure, in terms of pounds, that pressure, that atmospheric pressure, is approximately a little bit less than 15 pounds per square inch. So when you are under normal atmospheric pressure at the surface of the Earth, you are feeling 15 pounds per square inch, every square inch of your body. That kind of push. It doesn't bother you because you're used to it. Right? And you've adapted to it. What's that, Vicki? But actually great changes in that could give you migraine or something like that. If you have changes in that where you're not used to, physically used to that change, then that could be a problem. Okay. Take a look at this. I got a container of fluid. I'm going to focus in on a piece of this fluid. Just this can of fluid up there, which I've just kind of identified in the form of a can, but it's a piece of fluid within a fluid. All right? And we know that there's mixing going on and that sort of thing, but for the moment I'm going to say that I can focus in on this can of fluid within the fluid. As I look at that piece of fluid, I notice one thing. It's in equilibrium. Now, like I said, there's mixing going on, but for all practical purposes, this can of fluid within the fluid is in equilibrium, which means that the net force on it must be 0. Right? It's really not sinking on itself. I mean, it's not sinking down. It's really just kind of staying there for all practical purposes. So if I can say that the net force on it must be 0, that means there are forces exerted on it, on this can of fluid, but they all cancel out so that it doesn't move. Well, this is probably easy to prove horizontally. If I look at this piece of fluid horizontally, I can think of the fluid around it pushing on it from all directions. So for every force there is on this side, there's a force on this side. And they're, by symmetry, they're equal and opposite, and so one cancels the other. And I can think of those forces being all the way around this can of fluid. So on whatever side you're looking at, there's a force on the opposite side. They're all canceling out for the most part, so that it's not moving horizontally. What about vertically? If I look at this can of fluid, it's in equilibrium vertically as well, so that the net force on it in the vertical direction must be 0. There are definitely forces on it in the vertical direction. There's the force due to the pressure on the top, pushing down on it. That would be the weight of, in this case, the weight of the atmosphere over that cross-sectional area of the can. And that would be pressure causing a force, pressure times area. There would be the pressure on the bottom pushing up. That would be due to the pressure of the fluid on this area on the bottom, which is the same cross-sectional area. And the can of fluid also has its own weight. So there's a weight of the fluid itself, which is being pulled down towards the center of the Earth. these are the forces that are acting on this can. So I got the force of the pressure above it, which I'm going to call P naught times A. P naught just being the pressure at the top. I got the force of the pressure below, which is, I'm going to say that pressure at that moment, right at that depth, is P. So that force would be P times A. And then I've got the weight of the can of fluid itself, mg, pulling down. And as a result of these three forces, it doesn't move. So I can write that the summation of all the forces should equal 0. And I've got P times A plus a negative mg plus a negative P naught A equals 0. But the mass of the fluid should equal the density of the fluid times its volume. So I'm going to rewrite the mass of this fluid as the density times the volume, like I said I was going to do before. And the volume of this can is going to be its cross-sectional area times its height. So I'm going to substitute in for the mass, the density times the cross-sectional area times its height. I'm going to put that into that equation there. And now it looks like this. And I've got the cross-sectional area in all three of those terms. I'm going to divide through by the cross-sectional area, get rid of that, and simplify, and I get this. That the pressure at some depth is equal to pressure at the top plus rho GH, where rho is the density of the fluid, G is 9.8 meters per second squared, and H is the depth that I went down into that fluid, the depth from the top. The pressure at some depth, H, is equal to the pressure at the top plus rho GH. Oftentimes, if this were at the top of a container of fluid, the pressure at the top would be atmospheric pressure if it were open to the atmosphere. But it doesn't have to be that way. If we're in the middle of the fluid, it still would be the pressure at the top of that can plus rho GH to the bottom would equal the pressure at the bottom. So you can always think of this as the pressure at the top, but oftentimes that P naught will be atmospheric pressure that actually is at the top. This is a really interesting equation here. It relates pressure to depth. And one conclusion we would have of this, because we kind of did this in general, but it's true in general for any kind of situation we can imagine. Based on this, if you're at one depth within a fluid, say if you're in a body of water, and you're at one depth within that body of water, the pressure you feel at that depth would be the same anywhere at that depth. So if you're swimming around in some lake or in some body of water, and you're at the same depth no matter where you go, the pressure you feel at that depth is equal to the atmospheric pressure above the water plus rho GH, H being your pure depth into that water. So if you're swimming around and all of a sudden you find an underwater cave, and the cave is full of water as well, and you swim into that cave, you still feel the same pressure because you're still the same height below the top of the water. Independent of the container shape, so all points at the same height within a container of fluid have the same pressure. Pressure increases linearly with depth because this is a y equals mx plus b type equation. In other words, if h is our variable, because h is what's going to be changing, that's our depth in the fluid, it's equal to some constant, which is the pressure at the top, P naught. And our slope is going to be rho g, so our pressure will increase with increasing depth. The deeper you go, the higher the pressure, linearly. And we'll also note that at each constant height, your change in pressure at that point will equal your change in pressure above the fluid, or at the top. What does this mean? In other words, if I were at a constant height, if I stayed at a constant depth within the fluid, if the air pressure were to change above that fluid, then I would feel that change, right? Because my height hasn't changed. So my delta H would be 0. And so I'd have that any change I would feel above would be felt below, all the way through the fluid. Any change of pressure applied to the fluid is going to be felt all the way through the fluid. If you were a fish in the sea, you're swimming around, and you feel a certain pressure at a certain depth, and a hurricane were to pass over your point, you would feel the change in pressure due to the hurricane. Right? Because that change in pressure would be applied all the way through the fluid. You would feel that drop in atmospheric pressure that was occurring above the sea. So I guess the fish in the sea would know when there's a storm up above them. But more important than that, this idea of the pressure change being applied all the way through the fluid is the principle behind hydraulics. If you have a fluid, a hydraulic fluid, and you apply a pressure change at one end of that fluid, it's applied all the way through that fluid, and you can use that to your mechanical advantage. It's called Pascal's law. It looks pretty simple enough. In a wordy definition, a change in pressure applied to an enclosed liquid is transmitted undiminished to every point of the liquid and to the walls of the container. See how it might work for a hydraulic press. Consider this situation. I've got two pistons, and I have a fluid inside this container here. And one piston has a cross-sectional area of a certain amount. The other piston has a larger cross-sectional area. I wish to lift a real large mass that is on this larger piston over here. But I want to do it using a smaller force. What I could do is apply a relatively small force on this smaller piston. What that will do is apply a change in pressure on the fluid equal to my force times this cross-sectional area. That's what pressure is, force per area. So I apply a certain pressure on here, change in pressure, force per area here, and that is applied all the way through the liquid, all the way through the fluid, and to its walls. So my change in pressure applied here, force per area here, is equal to the force per area applied here. But that area is much bigger, so the force applied there is much bigger. In order to have the same pressure, in order to have the same force per area. So a little force here on a little area can equal a big force here on a big area. And hence, with a little force, I can lift something much larger. It looks something like this. Change in pressure at one equals change in pressure at the other. So the force per area at one equals the force per area at the other. And so the secondary force that is applied on the big piston is equal to the ratio of that area to this area times the force applied on the little piston. It almost seems like it's unfair. It almost seems like I'm getting something for nothing, doesn't it? If I apply a little force here and lift something that's a whole lot bigger. Can you explain that apparent paradox? That it looks like I'm getting something for nothing? Less displacement on the large one, correct. In other words, for me to lift this larger item, which is a lot more massive with a smaller force, I'm going to have to push the smaller piston a much greater distance. All right? So I don't get something for nothing. I'm going to apply a small force for a great distance because I'm really displacing very little fluid here. So even though I got a larger force here, it's not moving very fast. All right? Not moving very far. So I have to push with a little force for a large distance to get a big force for a short distance. And the work done is the same. All right? So there's no energy advantage, but there is a mechanical advantage in applied force. Let's actually put some numbers on this. Let's say I want to lift a car, and I'm going to apply a force on a little piston, and the larger piston is going to lift the car. Looks like this. A car lift using a service station, compressed air exerts a force on a small piston of circular cross-sectional area having a radius of 5 centimeters. This pressure is transmitted by a liquid to a second piston of radius 15 centimeters. What force must the compressed air exert in order to lift a car weighing 13,300 newtons? So I have the first piston, radius 5 centimeters, and the second piston, radius 15 centimeters. The force I need to apply is going to equal to area 1 over area 2 times force 2. Force 2 is what I want to lift. Area 1 is going to be the area of this circle. Area 2 is going to be the area of that circle. And I can keep them in centimeters because the centimeters are going to cancel out. So I'll have area of this circle is going to be pi r squared, pi times 5 centimeters squared. And the area of this circle will be pi times 15 centimeters squared. Pi's cancel out. And I'll have 1 over 3 squared, or 1/9. So I need a force of 1.48 times 10 to the 3 newtons, which is 1/9 the actual weight of the car. 1.48 newtons, or 1.48 times 10 to the 3 newtons would be about the weight of 2 adult human beings. So if 2 of us got on this small piston, then we could lift up the car. What air pressure will produce this force? Pressure is force per area. So that force, 1.48 times 10 to the 3 newtons, over the actual area of that piston, pi times 0.05 meters squared, needs a pressure of 1.88 times 10 to the 5 pascals. And 1 times 10 to the 5 pascals is about 1 atmosphere. So 1.88 times 10 to the 5 pascals is approximately 2 atmospheres of compressed air pressure. Here's another problem from your book. Calculate the pressure at an ocean depth of 1,000 meters, 1 kilometer. Assume the density of seawater is 1.024 times 10 to the 3 kilograms per meter cubed, and take atmospheric pressure to be 1.01 times 10 to the 5 pascals. So we're going to apply this pressure formula. Atmospheric pressure at the top plus rho GH to find the pressure at a depth of 1 kilometer in the sea. numbers. I have atmospheric pressure 1.01 times 10 to the 5, plus the density of water 1.024 times 10 to the 3 kilograms per meter cubed, times G 9.8, and we're going to go to a depth of 1 kilometer, 1,000 meters. So this would actually be 1 atmosphere plus 100 atmospheres, 1.01 times 10 to the 7 pascals, approximately 101 atmospheres. If I went down 1 kilometer in the sea, I would feel 101 atmospheres of pressure. A good rule of thumb, and one that you can possibly use for a lot of problems, is that for every 10 meters you go down in water, you add an atmosphere of pressure. 10 meters down in water is an atmosphere of pressure, 33 feet. So if you go down 1 kilometer, you're going down 100 sections of 10 meters. So you add 100 atmospheres.
How much can a human body bear?
Excellent question. Very glad you asked that question. That is being tested in very recent years. Let me tell you a story. There's a sport, and I didn't know this until recently. Deep sea diving, free diving. Okay? And it's a big sport, and there's like 20 different categories to it. And you can do different ways that you want to dive. And you can do just a pure free dive, just jump in with no help and dive, but that's not the most common way. The most common ways are one where you're going to set your records. It's called no limits free dive. I just learned about this recently. No limits free dive. And what you do in a no limit free dive is you can use help to get down to your depth. You just can't use any breathing apparatus. Right? So you have to hold your breath. So in a no limits free dive, you would get on what they call a sled. And the weight of the sled would pull you down to some depth. And then at that moment, you would let go of the sled and you would release a balloon. And the balloon would inflate and then pull you back up. Only to a certain depth, because you don't want to be pulled up too fast, because you would get the condition called the bends. You would get the bends. All right. More on that in a moment. But there's a whole sport in this. And in fact, world records have been set in the last few years. And there were 2 women who were competing back and forth in the Canary Islands. And one of them was Audrey Mester. And she held the world record for quite a while. She went 125 meters down to depth using free diving. 125 meters would be 100 or 12.5 atmospheres. So when she goes down, when she went down to that depth, she's feeling 12.5 atmospheres of pressure on her eardrums. Sometimes they blow eardrums and things like that because it's an incredible amount of pressure, very painful. Well, there was another woman, Tanya Streeter, who broke her record, broke Audrey Mester's record. And she went down to 160 meters, so 16 atmospheres. And she did it by practicing, so she would go down, 80 meters, and then 90 meters, and then 100 meters. And the people were trying to help her out. They didn't want to go down that deep. So at some point, she's going down by herself. I mean, they put divers down at every certain amount of distance for safety, but at some point, even the divers can't handle that depth, and so she's by herself, and she passes out, and that's it. Well, she didn't die. Tanya Streeter did not die, but she did kind of lose her bearing at 160 meters. She lost her bearing for a while, And then finally, she was able to hit the release on the balloon, and she came back up. It could only take you, the worst part of the bends is a condition where you've got gas that is dissolved in your blood. It's nitrogen and oxygen and other gases. And as you put your body under pressure, those gases get more dissolved into your blood. So you don't want to come up too fast so that those gases are released all of a sudden and you got these bubbles in your bloodstream. And that interferes with your bloodstream and doesn't make you feel very good. And the worst problem with the bends is not necessarily at the highest pressures. It's in that last bit where you're changing over the last few atmospheres of pressure. So you can actually come up relatively fast until a certain point, and then that last bit, you got to come up slowly so that you can equilibrate while you're coming up. Right? You can let this gas kind of just undissolve into your blood. Right? So, Tanya Streeter set the record, 160 meters. Her rival, who had the world record, Audrey Mester, tried to break the record right after that, and she died. And she drowned. Not a sport I would suggest you getting into. And since that time, there was a guy. His name is Patrick Muzumu. He's a Frenchman, Patrick Muzumu. And he theoretically, it's not official, but theoretically, and he has it on film, he died to 210 meters, 21 atmospheres of pressure. He died at 210 meters, and basically they were saying that that's near the limits of human capability. He used a special technique. Apart from, well, they all use special techniques. Before they dive, they hyperventilate to try to bring in more oxygen into the lungs. They said that after you go 50 meters or something like that, your lungs get to be about that size because they're compressed so much. So you try to put as much oxygen as you can into your lungs. His other technique was, as he's diving, he allows water to come into his sinuses and into his tubes, so he can equilibrate pressure before his lungs.
And then that's borderline drowning.
Yes. Yes. But somehow he's figured out some technique where he can do that and then expel the water when it comes back out.
How long does it take when you get down there and come back up? Like, what's the time period?
In order, if you are into this kind of thing, you probably would have to hold your breath for about 4 minutes, at least. I think Tanya Streeter, that's her big thing, is that she can hold her breath for more than 4 minutes, almost 5 minutes. So it takes about probably 2.5 to 3 minutes to get down there, and then you come up pretty fast, and then that last bit is probably the hardest thing because you want to get back up there, but then you have to come up slowly over that last bit. It's about more than 4 minutes when you be able to hold your breath. There's a whole sport in it. It's a whole big deal. Let's try this. Calculate the total force exerted on the outside of a circular submarine window of diameter 30 centimeters at this depth, say 1 kilometer depth. So if you were to go down in a submersible, and there's a little submarine window about 15 centimeters diameter, so 30 centimeters diameter, so about that big, like that. And you're looking out. What is the force on that window? The pressure is 1.01 times 10 to the 7 pascals. So if you multiply that by the area of the window, you would get the force. So that'd be pi r squared. force on that window would be 7 times 10 to the 5 newtons, 700,000 newtons of force on that window. An average adult human being probably would weigh about 700 newtons. So the force on that window would be the same as if you were up top and you had 1,000 people, each of them standing on each other's shoulders, 1,000 people standing on this little window. That would be the force of the window. There was a submarine, United States submarine called the Thresher. Have you ever heard of it? The Thresher? What do you know about the Thresher, Aaron? You know?
Here tonight, I'm sure you know pretty much.
The Thresher had a little crack in its hull, and it came into port, and they repaired the crack. They welded the crack, and then on its next journey out, it went out and presumably, and there are different stories about what happened. Presumably, it wasn't good enough, and so they went down to a depth a little bit more than this, I think, and something went wrong, and they couldn't get back up. So at some point, they just kept on sinking and sinking and sinking. At some point, the pressure of the water pushed through. And fortunately, for those who are on that kind of submarine, the death is pretty quick. Because when you have a breach of pressure like that, the water will just come in real fast, and it won't be like a torturous death. All these neat things for me to tell you today.
Except for the panic beforehand.
Except for the panic before, yeah. So we lost that submarine, 129 sailors on that submarine. But I think in our history we've only lost 2, and I think the Russians lost countless submarines. They weren't as safety conscious. How do sea creatures survive at extreme depths?
Is it the same way that guy did? They let water?
Basically, that would be it. Same way the guy did. They basically would let water into their bodies. All right? Because anytime you try to enclose yourself against the water, you're creating a problem because you're allowing a pressure difference between your inside and outside. But if you allow the water into you, then you allow that pressure to equilibrate on both sides, and it's no problem. So the creatures that are actually living at great depths actually are kind of thin-skinned, and they actually have mechanisms where they actually bring the water into them and kind of equilibrate against the depth. Pressure measurements. Let's skip this one. Here's a barometer, a mercury barometer. Let's see how a mercury barometer might work. I've got a reservoir of mercury. Right? It's open to the atmosphere. So on this open part of this reservoir, atmospheric pressure is bearing down on its surface. Right? So that's what that P naught is. That's atmospheric pressure bearing down on the surface of the mercury. But I also have a tube also filled with mercury. And what I've done is first I filled up the tube with mercury, and then I flipped it into the reservoir. So that when the mercury within that tube is basically settled, I don't have any gas at the top of that tube. In other words, when I flipped it over, the mercury being a very dense liquid that doesn't dissolve gas too well, when I flipped it over, it basically left a vacuum at the top of that tube. No gas in there. All right? So far, so good. So what I could say is at the top of that tube, the pressure is zero, because it's in a vacuum. There's no pressure. There's no air pressure. At the bottom of this tube, at point A, the pressure is atmospheric pressure, because I said that if you're at the same level within the same fluid, the pressure is the same. So if I'm at, even though the pressure here is atmospheric pressure, then at the same level, even at the bottom of this tube, at this point A, it's atmospheric pressure. If you're at the same level, it's within the same fluid, the pressure is the same. So, if we look at this column of fluid, pressure at the top being zero, pressure at point A being atmospheric pressure, and the column is some height h in length, then applying our pressure formula, we'd say pressure at point A is equal to the pressure at the top plus rho gh. But the pressure at the top is zero, so the pressure at point A is equal to rho gh. But the pressure at point A is atmospheric pressure because we're on the same level. So I would say atmospheric pressure is equal to rho gh. Rho being the density of mercury, G being 9.8, H being the height of that column. Right. The density of mercury is constant, G is constant, 9.8. So what I've set up here is a way to measure the pressure of the atmosphere based on the height of this mercury column. And I could graduate that column for different pressures and calibrate. That's basically a mercury barometer. The reason you'd want to use mercury, even though it's toxic and dangerous, the reason you'd want to use mercury is because it's the most dense liquid that we have. And so your column wouldn't have to be so high. I mean, atmospheric pressure would be 76 centimeters. So you'd have a column of mercury near that high, at 76 centimeters. And the other thing with mercury is that, like I said, it doesn't dissolve gas very well. So it would protect the integrity of that vacuum. As opposed to water, if I used water, then this barometer would have to be 10 meters high. It would have to be 33 feet high. Right? And water dissolves gas, so it would start immediately disintegrating that vacuum, and it would not be a good barometer at all. I'm going to stop there.